the most common, kind of the default metric for real valued features is the Euclidean distance. You might also hear it called the Diliatou norm. It's basically just the simple straight line distance you learned about in geometry, calculated as the square root of the sum of the squared differences between the feature coordinates.
But I know there's another common one too, the Manhattan distance, or L-1 norm. Why do we usually default to Euclidean, the tool L-2? Is there a specific reason?
Ah, that's a great technical point.
Hmm.
Yeah, the Manhattan distance, L-1, it sums the absolute differences. Think of it like calculating distance if you could only travel along grid lines, like walking blocks in Manhattan. Now, while the 1 is sometimes useful because it's less sensitive to outliers, but Euclidean metric is generally preferred. Why? Because it creates a smoother, more mathematically convenient distance space. That squaring operation in L-2 naturally emphasizes the bigger differences more dramatically, which usually helps distinguish close neighbors from really distant ones more effectively.
Makes sense. And since this whole algorithm hinges entirely on measuring features, I imagine you really need to trap the input data carefully, right?
Oh, absolutely. Feature scaling is basically mandatory for KNN. Think about it. If you have two features, say income measured in tens of thousands, and age maybe from 0 to 100, that income feature, just because its numbers are so much bigger, will completely dominate the distance calculation. Age will barely have an impact. So to prevent this, you must normalize or standardize all your real valued features. The goal is to get them onto a similar scale so they contribute more or less equally to the distance calculation.
Okay, good point. And what about discrete features? Things like color, maybe, or yes-no attributes. How do we measure distance there?
Right. For discrete features, we switch gears. We typically use the Hamming distance. This metric is pretty simple. It just counts the number of positions where the corresponding symbols in two strings or vectors are different. So if you have red, yes, large, and blue, yes, large, the Hamming distance is 1 because only the first feature is different. It's a really effective way to measure similarity in that kind of categorical space. And critically, the sources also mention you can assign weights to features when computing distance. This allows you, maybe through expert knowledge, to say, hey, this feature is way more important, and give it more influence in the similarity calculation compared to less important ones.
Okay, now we get to the really crucial hyperparameter,